So for probably years now, you've been graphing things the same way, right? If I give you some point in space, you figure out whatever the x distance is to the point, and then you figure out whatever the y distance is to the point, and you have some point x, y, right? Simple enough. You just go over that many spaces, you go up that many spaces. But that's actually not the only way to think about points. It's just a very convenient way to think about points. But it's not always the most convenient way. So for instance, it might be easier if in some cases you were just told, if somebody pointed you in the right direction and said walk 10 steps once you're in the right direction, then you'll get there. That can be a lot easier than going, okay, well, I need to walk 4 steps up and then I need to walk 5 steps over, that sort of that wouldn't equate to the same thing in this case. But the idea is it could be difficult to navigate. It's sometimes a lot easier just to go, all right, look, turn to your right, 30 degrees, and walk. And the idea behind a polar coordinate is exactly this. What it says is, I got the same point, but instead of thinking about it in terms of walking a grid, so sometimes this is this sort of grid, think of like a major city, right? If you were in Manhattan, you would go over and up, and that's kind of how you would get from places. But if you're thinking about sort of, as they say, as the crow flies, well, the crow is not, he doesn't have to move around buildings, he can fly over them, so he just knows where he's going and goes at it. And polar coordinates work that way. You just say, all right, I can figure out how far up that point is. So if I'm in like a 3D case, which we're not doing, you just sort of find it. You do 2 angles. You look over and up, and then you go to it. And that's the idea behind a polar coordinate. So I'm saying a lot here, but ultimately that's all polar coordinates are. They're just thinking about points or locations in terms of kind of where is it at and how far away is it, as opposed to thinking in terms of some gridded situation. So again, in this case, we say this r is a distance from an origin to the point. And then if you take a direct line to that point, and you take the angle it makes with the positive x-axis, that gives you what theta is. So instead of xy, we have r theta. So notice in this case, we still have 2 dimensions. So instead of an x dimension and a y dimension, we have an r dimension and a theta dimension. So, and those are not, they're not the same in the way you think they are. So like in xy coordinates, how you're used to, you could think of, just a bunch of lines running this way, and a bunch of lines running that way, and you have a grid. So really x and y are kind of the same thing. They're just, one has horizontal lines and one has vertical lines, right? Not that big a deal. In polar coordinates, it doesn't really work that way. So if you think about everything, like in this case, if I think about the line x equals 1, where x is fixed, then that's just a vertical line because it's all the possible y values, but x is fixed. And if I said like y equals 2, y is fixed and all the x values go left to right, so it's a flat line. But in polar coordinate space, or theta space, if I say all the places where the distance away from the origin is 1, well, think about all the ways you could be a distance away of 1 away. You could be a distance of 1 away here, 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 here. You have a circle. So instead of the strips being lines like they are for x and y, the strips in r space are circles for r. And then if you think about all the thetas, you say, all right, what about all the cases where theta is pi over 4? Well, then r could be 1/2, it could be 1, it could be 3, it could be 1,000. So the theta spaces are actually lines. They're all lines, but they're lines through the origin and they rotate, as opposed to kind of on x and y, they're just, they're gridded out. And then, so you have these circles, these concentric circles for r, and you have these sweeping lines for theta. And that's a little bit odd. That can cause trouble sometimes when people are trying to understand this. But, sorry, I can see I'm kind of fuzzing out here, so maybe this will clear up, or maybe I need to walk. Hey, it did. All right, so One thing that you need to note is that, again, these are representing the same things. So the representation of r theta, where that's a point, and the representation of x and y, they're not just similar triangles, or equivalent triangles. So as a result, we can use trigonometry to draw some really good conclusions. So if I have x, y, r, and theta, right, I can add those over here. Then I know x squared plus y squared equals r squared, right? Because this is a right triangle situation. It's a right triangle here. And this is clearly a right triangle because you're slicing the square in half. And so r squared equals x squared plus y squared. Okay, that is the relationship of those two variables. It's often used for what's called coordinate conversion, where we're trying to change between the styles. And then similarly, if this is theta, then tangent of theta is y over x. And you have to be careful. If the x coordinate is 0, then this doesn't make a lot of sense. Yeah, so if the x coordinate is 0, you're going to have some issues. But if the x coordinate is not 0, then you're fine. Now, let's see. Alternatively, we can use the same triangle. So r, so if I said sine of theta, it would be y over r. Another way to say that is y equals r sine theta. And then if I took this theta here and I said cosine of theta, it would be x over r. So cosine of theta is x over r, or if I multiply both sides by r, I get x equals r cosine theta. So these are really huge. These are big deals because they tell you how to go from one to the other. Because sometimes it is convenient to do things in polar space, and sometimes it's not. So it really just depends on it really just depends on what your application is, honestly. Now, other things you might need to know about polar coordinates that's really neat is that polar coordinates have some kind of duplicate representations. For instance, r and theta is equal to negative r and theta plus pi. So let's think about this for a moment. I mean, you might understand that intuitively. Let's say you didn't. So if I was standing, let's say I'm standing right here in front of the camera, and I'm trying to walk 2 steps forward. So my angle at this point is maybe 0, because if I considered 0 dead on to the camera, and I want to walk 2 steps forward. So I could walk 1 step or 2 steps forward, or I'm sorry, I could walk 2 steps forward. Now, alternatively, what would happen if I were to turn completely around? Right, so then, I just want to make sure I'm talking to the camera. Then I could take 2 steps backwards and be in the same place. Right, the idea is it doesn't matter if if you see that's what's exactly happening here. If I'm dead on and I take 2 steps forward, if I turn around completely, right, 180 degrees, and walk backwards, I'm doing the same thing. That's what this means. That's all this means. So what does that mean? Well, what it says is that if for some reason your r ends up negative, you can change the theta by 180 degrees and make r positive. So a lot of times that's a lot easier to deal with. Sometimes it actually is convenient to do it this way, but it's not common. A lot of times you're actually trying to get back to something like this. And finally, r theta is equal to r theta plus 2 pi. And that makes a lot of sense, right? So if this is my angle, and so I'm at this fixed angle, and then let's say I rotate 2 pi. Well, 2 pi rotation, I'm back to where I started. So it doesn't matter what angle you start at, you can always add 2 pi or subtract 2 pi and be at the exact same location because you're just doing one turn around the circle. So if you do a half turn, you're pointed in the negative direction. If you do a full turn, you're pointed in the same direction. And we're going to do several examples, not only graphing things, but converting those equations back and forth. And realistically, we're just going to be using these things right here, and we're trying to get a better feel for polar coordinates just in general.